Hello, everyone. Thanks for coming to the PIBBSS Symposium 2024. Our next speaker today is Yevgeny Liokumovich, and who will be talking about singular learning theory and finding minimum description length for singular models.
Thank you so much.
Yeah, just one few more things. The talk will last probably about 40 to 45 minutes. And if you have any questions, you can use the Q&A function. There will be up to 15 minutes time for asking questions and talking to Yevgeny at the end. And also when all our speakers today present their work, you will have an opportunity to join the breakout rooms to talk to them one-on-one in a more unstructured way. So, Yevgeny, go ahead.
Thank you so much, Mateusz, and thank you to Matthew for an excellent talk. It's a great pleasure to be giving a talk in this symposium. So let me start with some words of warning. So I'm a mathematician working in geometric analysis, and the stuff that I'm going to talk about today, I'm very far from being an expert in these things. These are, so this PIBBSS program was a wonderful opportunity for me to dive into it, and I'm very excited about it. And I've really learned a lot, but I am not an expert, and a lot of the stuff would not be possible without conversations with Alexander Yettelin-Goldenziel and Simon Peppenle-Haller, who gave me a lot of reading suggestions and ideas and directions for the proofs. And Clem was also a great support. And yeah, thank you for wonderful PIBBSS team. Let me also mention that I have this fresh positive COVID tests, so there will be some coughing and brain fog on my part today. So we will start with a certain classical observation, which goes to the foundations of the subjects of machine learning and information theory. So suppose we have some collection of data given to us. So what can we do with this data? Here are three different things that we could do. We could try to compress this data, or in other words, we could try to find the shortest description of the information contained in this data. We can also ask about predicting the next element, right? So if this is x1 up to xn, then what is xn plus 1? Right? And then if this data is, for example, pictures of cats, you can try to build a machine. That's a terrible cat. That takes this data in and learns what cats look like. And so the classical observation is that all of these three things are actually just the same things. They're just different ways of looking at the same problem. Okay, so each of them has the associated kind of subject which studies it. So the compression would be information theory, and prediction would be statistics. And today we're going to talk about Bayesian statistics in particular. And here we have machine learning. Sorry, my kids are a little bit loud in the background. If you want to compress data, then that requires finding some regularities in this data. And if you want to make a prediction, that also means that we would need to uncover some hidden structure that will allow us to make a prediction that's not random. And this is also what we want if we want to learn from data. So we have these three different things, but really they're just different ways of talking about the same thing. Okay. So this is the observation that these are just different ways of formulating the same problem. And let me be maybe slightly more precise by quoting a couple of classical theorems, classical results. So there's a classical theorem of Shannon from 1948, which says that if you have a probability distribution on the space of n tuples of data, then whatever code you pick to try to encode this information, encode this data, the best thing you can do is to have the code length of the size minus log of the probability for this data. So it's, the expected code length is the expectation of minus log of the probability, which is known as entropy or Shannon entropy. And another theorem making this connection, which is the Kraft inequality, which gives us a dictionary to go back and forth between probability distributions on a collection of n data points to encodings, right? So if you have a probability distribution, then you can construct an encoding of the property that the code length will be equal to minus log of the probability. And conversely, if you have a probability, then the code length and conversely, if you have an encoding, then you can define a probability distribution on your data, which satisfies this property. So basically, what this tells us is that we can go back and forth between the problem of trying to find a coding and encoding for our data of a certain code length and defining a probability distribution. And so if you think about the graph of minus log of p, so you see that what's happening here is that finding a probability distribution that assigns high probability to the data that we see is the same thing as finding an encoding that has a short code length. Okay, yeah, and please feel free to interrupt me with questions at any moment. So next, we will try to find a probability distribution or an encoding corresponding to this data using a bias theorem. And so Bayesian approach to the construction of this probability or a base code length is to consider a certain family of probability distribution. So we have some d-dimensional manifold. You can think about it as a subspace of a d-dimensional Euclidean space. Often this is the situation we're in. And here, every point in the space corresponds to some probability distribution. So before we are given the data, we don't know. Yes, so this is some. This is some probability distribution on X. And before we are given the code, we don't know which one of these works well, but these are our guesses, right? So we have some family of potential probability distributions that we would like to use to describe this data. And we also have some function, some prior, which is our guess about which in this family, which probability distributions in this family are more likely and which are less likely to be useful for this data, right? So we start with some initial large variety of probability distributions, a large dimensional family of probability distributions that we'd like to then use to describe our data. And then the encoding that the Bayesian approach gives us is this integral, Bayesian marginal likelihood, which is equal to the integral of the prior times the products of probabilities. Yeah? So we take the products of probabilities corresponding to each of these points, and then we integrate over a whole parameter space. Okay, so this is the Bayesian approach. And then the corresponding code length is just the minus log of the Bayesian marginal likelihood. It's also sometimes called the free energy because of similarities with physics. And then in the setting, we have the following result. So there are different formulations of this result in different settings. So this one that I state is due to Clark and Barron from the 90s, and certain other formulations were given by Rissanen. So I'm kind of here zooming in onto the simplest simplest possible formulation here. So if we have a sequence of data points that are independently and identically distributed and are generated by a probability distribution, which is one of the probability distributions in our family. So such situations are called realizable. And we assume some regularity assumptions, which we will come back to a little bit later. It turns out that they're quite important about this family of probability distributions. Then the expected code length, well, we have the following expression from it. So, well, this term, we have to have it, right? The Shannon's theorem tells us that we will have at least that. But on top of that, we have these other terms. Here you can see the dimension of the parameter space come in. So if you have a larger dimensional parameter space, then the code length will be larger. Then we have the term which involves our choice of prior. And then we have a term which involves the value of the Fisher information matrix at the true parameter. And then there is a term that goes to 0 as n goes to infinity. Okay. Well, there is still one degree of freedom here, which is we haven't exactly decided on how we're going to choose our prior. What is the right way to choose the prior? And well, this is kind of a very naturally occurring question, because if you think about our family of probability distributions, we can define a slightly different family. So if I have a family parameterized by a disk, I can take a small little disk inside it, and then I can consider a function f, which is going to push this disk outside, and it's going to shrink the annulus. And so then what this map does is it expands the little disk and shrinks the annulus. And this is going to be our W prime. So we will have then here a family of probability distributions parameterized by this space W, and then we'll have this family of probability distributions tilde, which is just P of X, F, W, parameterized here. And well, these are the same family of probability distributions. All the probability distributions are the same. However, if we try to pick a uniform prior, right, which would be maybe the first guess that you make, just give the same weight to all of the probability distributions that you have, then, well, here you will be giving small weight to this, and here you will be giving large weight to this. So the question of which prior to choose is also a question of, well, what is the correct parameterization for this family of distributions? And so then the natural thing to do is the following. So, well, let's try to measure how many distinct probability distributions we actually have in each region. So this is our W. So let's pick a maximal collection of points Pi here, Pj, rather Wj, so that the KL divergence between any two of them, Pwj1 and Pwj2, is going to be greater than some number delta, right? So in some parts of our space, we will see that, you know, the probability distributions change quite fast, and you can actually pack a lot. And in some parts, it could be much more sparse. And then we can try to define our prior in such a way that if you have this set U, then the integral of phi over U will be proportional to the number of WJs, right? So we would measure how many distinct probability distributions you actually have, and then take this delta to 0 and see what kind of prior this gives you. And so the kind of prior that this approach gives you is known as the Jeffreys prior, and it's just going to be a square root of the determinant of the Fisher information matrix with the normalization constant. So that's one way of choosing the prior. But there's another way where we would like to say, okay, so we want to minimize our description length of our data. And we would like to choose a prior, because we're choosing the prior before we've seen the data, we'd like to choose it in a way that minimizes it over all possible things that we could see. And it's a result of Riesen and Starkov that in various, again, settings here, I'm making some regularity assumptions, some important regularity assumptions, that this also leads to the choice of the Jeffreys prior. So from both of these points of view, Jeffreys prior is the correct way of defining the prior. Except it turns out that from the perspective of machine learning of today's AIs, it's the regularity assumptions are not satisfied. Okay, so let me wait. So we haven't gotten there yet. We'll get there in a second. So what happens if I plug in? So we made this choice of the Jeffreys prior, and then before we had this formula for the expected code length, and so we can now plug in the Jeffreys prior into here and see what we get. And so if we do that, then this is the expression that we have. And if you look at these three terms, then you see that it now gives you a criterion for model selection. So if you have similar, so this is just going to be the loss at the maximum likelihood number. So if you have this first term comparable with two models, and the next thing that you look at is the log term, right? And then given similar loss, what you want to do is you want to select a model which has smaller dimension. And then if between two models with similar dimensions, you want to look at the integral of the square root of the Fisher information matrix and pick the one which has fewer distinct probability distributions. So this now gives you a kind of a mathematical formulation of Occam's razor. You're picking the model which is simpler. It has smaller dimension, it has smaller number of probability distributions. And then you can also try to understand this term. There's a very nice paper by Balasubramanian, which computes terms that go to 0 as n goes to infinity. And this also has some interesting interpretations in terms of the curvatures of your parameter space. However, the issue that we have here is that there's a key assumption that we've made, which was that there exists a unique point W0, where the function k of W, which is the KL divergence between the true distribution and probability distributions in our space, is minimized. And if you look at the neighborhood of that point, then k will look like that. So k will be a Morse function. It will be a function so that wherever you go, it's the second derivative in every direction. The second derivative is non-zero. So the Hessian of k is non-degenerate. And it turns out that this assumption is not satisfied in a major way for neural networks. Okay, so let me quickly say about the neural networks and how do we translate between this Bayesian setting and the setting of neural networks. So So say we are given a feed-forward neural network of depth L, and W here denotes the coefficients of all of these linear affine functions. And here in between, we'll have a pointwise application of some nonlinearity. So sigma has some activation function. For example, hyperbolic tangent or ReLU. Okay, so we would like to find the coefficients that best fit the data that we have. So we have some correspondence between Rm and Rn, some pairs, and we would like to find the best way to do that. And so we can define a family of probability distributions that looks at the difference between the output of our neural network and if you if you feed it X and Y and assumes Gaussian noise, then this will be a natural model for this probability distribution, and then we can compute the Fisher information matrix in this case. And then if you do the computation, you'll see that for almost every parameter here, you will have that this is highly singular. And also empirically, for example, if you look at various computations of the Hessian of the for neural networks like this. So this is from a paper of Sagun, Batu, and Lioukoumovich from 2016. You can see that the Hessian matrix, which is equal to the Fisher information matrix of the true parameter, here is highly, highly singular. You have very few. So pretty much all the eigenvalues are very, very close to zero. And you have very few non-zero eigenvalues. Right, so this is the setup in which we have to work, and in which all of this previous beautiful theory, unfortunately, breaks down. So what can we do in this situation? In this situation, we'll have to work in the setting where this function is minimized not at a point, but on some subset. And along this subset, right, so instead of this kind of picture, right, we have a picture which is maybe something like that, right? And this set W0, which minimizes scale divergence from the true distribution, is going to be some possibly quite complicated subset. And then if you move in that direction, if you move in direction along W0, then of course your eigenvalue is going to be zero. So it's going to be singular in that direction. And so in the setting, there is a wonderful theory that was developed by Sumi Watanabe in the late 90s and early 2000s, which gives you a different description for the, which gives you a different formula for the minimum description length, where instead of the dimension D, you get a different number here, which is a kind of an effective dimension of your model near here. So this is known as the real log canonical threshold, and a certain invariant of the function k at its minimum point. It's also known as the learning coefficient. Okay, and so if you now think about the model selection story from before, you can see that this model selection story contradicted things that we know about neural networks, that as you increase the size, increase the number of layers, increase the size of layers, the generalization performance improves, right? And that contradicts the idea that you want to pick the smallest possible model. Okay, so right, so the thing that I'd like to say, though, is that in this talk, we are interested in this constant order term here. So the log n term is very, very small. So from practical considerations, it doesn't really play a role here. But the constant order term for small numbers of, or intermediate numbers of n, actually is expected to play an important role. And unfortunately, in Watanabe's result, it's quite hard to make sense of what it is, of what this constant order term is. So we will make a certain simplifying assumption, which is that we will assume that W0 is a submanifold of W, right? So, yeah, instead of a point, which is the regular case, we will assume that it's a certain D minus D dimensional submanifold. So this is because the dimension that we will be interested in, which is kind of the effective dimension of the model, is the codimension of W, which is going to be this little d. And so we expect it to be, so in particular in the setting, this is going to be equal to little d. And there is experimental evidence that in many cases of interest, this is something on the order of 0.01 of t, of the whole space of parameters. Okay, so we have this set of zeros, and then the minimum of k. And our assumption is that if you go in the direction perpendicular to this minimum submanifold, then the Hessian is non-degenerate, right? You will go up quadratically. So the eigenvalues of the Hessian in the direction perpendicular to W0 are going to be non-zero. So such functions with these properties are known as Morse-Bott functions, and we will call this a Morse-Bott assumption. So, so the result that I proved was directions and ideas from Simon is that in the setting with the Morse-Bott assumption, we have the following expressions for the code length. So this looks a little bit technical. It's quite a bit to take in. So let me concentrate on the realizable case here. So the realizable case is the situation where the true probability distribution is equal to one of the distributions in our family. And then in this setting, we have this formula where here, instead of the large d, we have this little d, which is, could be in some examples that we see is about 1% of the total dimension of the parameter space. And then we have this additional term, which involves the this d determinant, which is just the product of d largest eigenvalues of the Fisher information matrix, right? So most of the eigenvalues are going to be 0. So we pick just the largest d counted with multiplicity, and we multiply them, right? So that's going to be the determinant of the portion of that's going to be the determinant of the Hessian or in the direction perpendicular to W0. Okay. So then this expression inspires us to try to define an analog of Jeffreys prior for singular models. And the simplest setting in which we could do this is a situation where we have this large dimensional parameter space, but secretly the probabilities that are contained in this parameter space are really just correspond to some much smaller dimensional parameter space, right? So you can imagine that there exists a certain map into a smaller dimensional space, right? And the pre-image of that map is going to be this submanifold. And this would be an example of a highly singular situation, but by Sartre's lemma, for almost every point in the image, we will see that the pre-image, if the pre-image is our W0, then it will satisfy the Morse-Bott assumption, right? So if there's a way to somehow chop up our parameter space so that along those leaves of the slicing, the probabilities don't change. And then we somehow reduce the dimension of the of the whole space. And so in this setting, we can define a singular version of Jeffreys prior, which will be the d-determinant of the Fisher information matrix, square root, and then divided by the volume of the leaf in which it's contained, right? So if you have a large dimensional parameter space and you have this hypersurface, so that, or some submanifold, not necessarily codimension one, but some submanifold, so that the probability distribution doesn't change along this submanifold, then this notion of Jeffreys prior gives weight to this point by looking at the determinant of the square root of the determinant of the Fisher information matrix in the perpendicular direction divided by the d minus d dimensional volume of the slice you're in. And then in the setting, we obtain this result that tells you that if you have this large dimensional parameter space fibered over regular smaller dimensional parameter space, and we are in the realizable case, then this Jeffreys prior gives us the smallest possible worst regret in the same way as the usual Jeffreys prior gives us in the regular case. And then we obtain this expression that you can think about, again, what these various terms here mean. So here we have the entropy, this is the unavoidable term. Here we have this term which depends on the dimension. And here we have this interesting term where the larger the volume of the leaf, in which this point is contained, the better. So somehow you want to pick a model which is foliated by large dimensional sets of constant probabilities. So it tells you that these models are somehow the simpler ones, or these are the ones that having small description length will favor. Okay, so this is a description of results. Some of them may sound somewhat technical, so let me mention why should we care about these things. So the first reason why I got interested in it is because of was reading a lot of interesting developments in the developmental interpretability. And so, as I mentioned before, we have this model selection problem where you look at two different models, you look at their dimensions, you look at various other properties, and you pick the one that gives you the smaller description length. Here, the choice is made by a person. And so the idea of developmental interpretability is that because for singular models, we will have different kinds of effective dimensions in different parts of our parameter space, then if we have a learning algorithm which works very well, that means there is some good model selection that happens intrinsically. And we don't quite understand how it works, but here's a theory that tells you that this is the best way of doing model selection. So if you have if you're looking at some parameter space and then there is a phase transition to a different point in the parameter space, then this better solution should correspond to some improvement in the code length. Here. And if we can understand how those jumps, how those phase transitions, like rocking, happen, and we can quantitatively measure these things during training, then it gives us much better understanding of development of new capabilities of AI, and lets us anticipate increases in capabilities or possible emergence of more dangerous capabilities in a quantitative way. And another motivation was a fairly recent paper by Dalrymple and others on towards guaranteed safe AI. And there it's underlined that better understanding and more efficient algorithm for estimation of Bayesian posteriors is really crucial if we want to provide safety guarantees for our AI models. And I think better theoretical understanding of that is important for us to be able to prove that certain dangers, that certain risks really do have low probabilities, and that's also something that Yoshua Bengio advocates in his work. Okay, so I think I'll finish a little bit earlier with just mentioning some next steps that I'd like to focus on. So first, those formulas are nice, but I'd like to be able to find algorithms that will let me estimate, actually compute those singular Jeffreys priors. And the main thing to try to understand is, if I have a model, well, I'm not actually given this function f, right, in my parameter space. I need to somehow estimate, how large are these submanifolds of constant probability. And so there are some interesting papers that I've started looking into on estimating the volumes of these fibers, which is something that we'd like to do if you want to compute the singular Jeffreys prior. Another big question is, how good is the assumption that I've made, right? So in general, singularities of analytic functions can be extremely complicated. There is a lot of very subtle structure, and in particular, RLCT is quite difficult to compute, right? But so of course, every function can be perturbed into a Morse function, but this destroys the effects that we see at the intermediate values of n. And so one can first perturb a function into a Morse-Bot function and then perturb it into a Morse function. So Morse-Bot functions have a chance of actually not destroying the important structure. And in some of the examples in the work of Watanabe, he gives examples where we see, the posteriors concentrating not around the point, but around some kind of curves, right? And so, so away from those endpoints, here we do see something like a Morse-Bot structure. And so maybe Morse-Bot approximation is good enough for many practical purposes. And if that's the case, that would be very nice, because we wouldn't have to work much harder to understand the complicated structure of singularities. And so then it would be very interesting to see if we can detect phase transitions in neural networks, which would be, the situation where, going back to the formula here, right? So we could have, situation where the loss is similar, but there's a jump to a point where W0 has a smaller W0 perp has a smaller dimension, and W0 itself has a larger dimension, right? So this is what would be predicted by this expression. But we could also see a different type of phase transition where the dimensions are the same and the loss is the same, but there is a difference in terms of this other value, right? So if you separate our parameter space into parts and compute the integral of the square root of the d-determinant divided by the volumes of the fibers. So there could be a jump where we go into the part which has larger volumes of this fibers of this foliation. So it would be very interesting to try to detect something like that, and it would be helpful in, for understanding of changes in AI during training. Okay, so let me finish here.
Thanks.
Yeah, we seem to have quite a lot of questions from Alexander Gio, so I will just allow you to talk, Alex. You can unmute yourself now. and then just ask.
Sorry, I saw them just only now.
Yeah, no,
Perfect.
it's fine.
Perfect. Yeah. Maybe the first question is not so relevant. I was wondering, you refer to experimental evidence when you say that the learning coefficients is on the order of like 1% of the face of the parameter number of parameters. What exactly are we
I think I
referring?
was thinking about the paper by maybe a fairly recent one by Zach Furman and Edmund Lau.
Oh. So that's
that-
for linear networks, that is. Or
That's estimating the local learning coefficient at scale. Yes, yeah, for deep linear networks, that was the one. There was a paper by a group of people from UPenn, which also, although I'm a little bit more, I don't understand their methodology that well.
I see.
But they also
my understanding is that it is open. Like we don't actually know the global learning coefficient for like large models. I mean, there's some special cases, like you say, and with an estimator, you can sort of say things about relative things.
Right.
Yeah, I mean, yeah. So, I don't know, but I mean, of course, the Hessian often, if you just look at the Hessian, it has many zero
Right.
values. I think maybe that's also something on the order of 100 or something. Yeah. Then I had two other questions, a couple other questions. One is this.
I don't think that the parameterized models in Shaway-Lin's thesis are the same thing. But maybe I need to look at it more carefully.
Sure.
It's not.
Sure.
Yeah. If you maybe mean some specific, yeah. So at least what I've read is different.
Sure. Okay. Yeah. That's fine. Yeah, I was of course wondering. There's this sort of upcoming jet scheme story that Simon is investigating, and it's very exciting. And it is maybe more of a sort of. It's closer to some differential geometric intuitions. Maybe, I don't know. I was just wondering if you thought about.
Yeah, that would be really interesting to try to do. But it's in terms of definition of Jeffrey's prior, it's quite tricky. If you would like to give non-zero weights to
Sure. Okay.
corresponding to different
this is a big
dimensions.
question.
Yeah. So for this, in this case here, the way we define it is that for regular points, it's clear that this is going to be non-zero, right? And we just set it to be zero at critical points.
So your suggestion for the generalized Jeffrey prior, let me ask you one more question about that. So in the usual Jeffrey prior singular point, the problem is that singular points are assigned zero. They're assigned zero prior weight, which is obviously bad. It's sort of but in your revised version, in this special case, are singular points, do they get more volume, or more prior weighting or less prior weighting, depending on how singular they are?
So with this definition, we have that if you have a fibration like that, or more generally, you could also have foliation. So a family of these submanifolds, which not necessarily comes from a map. We have that the Fisher information matrix is equally singular everywhere, right? It's all of it has exactly, if you count with multiplicity, it has exactly d non-zero eigenvalues. Right, and this is what you get for all regular points of this map. And then the points that are more singular, they are the Jeffreys prior would give them 0 here.
They're still assigned 0 value.
They're still assigned 0, right? But you could try to play some games where you subdivide into some parts, and maybe in some part you have a foliation by leaves, which have high dimension, and another part lower dimension, and so you can define different Jeffreys priors on these different parts.
Okay, I
and
see.
Try to make sense of how to compare them.
Interesting. Thank you very much, Yevgeny. I think there's one more question from Rich Maxine.
So how much and what do we know about why neural networks learn general functions? Yeah, I don't think I'm qualified to answer that question. Maybe someone else wants to say.
Yeah, Alexander, you're already on.
Yeah, I mean, there are various. So it's a bit so the question is a bit ambiguous, can mean multiple things, but so there's a well-known experimental paper, it's called Zhang et al., which trains neural network on random data and shows that it can easily fit random data. And more generally, neural networks are very expressive. They're like way more expressive than is really needed, in the sense that if you look at actual like real life realistic data that comes from interesting sources, it is actually much less general than the sort of most general functions that the neural network architecture can learn. So there's an example. If you look at real neural networks, these are piecewise linear functions. And in general, the number, so it means you have the input is divided into little regions. On each region, it's a linear function. And in general, if you choose the parameters in general, this is going to be, there's going to be an exponential number of linear regions, exponential in the depth. So these can be very complex. But what we see in practice, if you actually look at realistic data, this is linear in depth. So to answer your question, I would say there's sort of 2 answers. One is neural networks can at least express very general functions. However, that's maybe not the interesting thing. The interesting thing is that real data is very structured, and neural networks have learned them quite efficiently, in a way that where they sort of this looking at all functions or all general functions is maybe a bit misleading, both experimentally and theoretically. Yeah.
If we don't have more questions, I guess it's time for a break.
Thank you.